In this lecture, I'll talk about the relationship between domains of holomorphy and the Dolbeault operator. So specifically, I want to talk about this result here. So if you pick an open domain in C to the n, then omega is a domain of holomorphy if and only if all the 0Q Dolbeault cohomology groups vanish in omega when Q runs from 1 to n minus 1. Now recall the Dolbeault cohomology groups were nothing but the kernel of the Dolbeault operator on 0Q form over the image of the Dolbeault operator on 0Q minus 1 forms. So I'll show this, I'll try to show the reverse direction of this theorem and talk about what needs to be accomplished to get the full characterization. And I will be aided in this by proving first two short lemmas. So lemma 1 here, lemma 1 says that if you pick any hyperplane in C to the n minus 1 dimensional subspace of C to the n, and for this case, let's just assume that the 0,1 Dolbeault cohomology vanishes, then every holomorphic function on the hyperplane intersected with omega extends to omega, right? So there exists a holomorphic function on omega such that the restriction of f onto L intersect omega is small f. Okay, so let me real quick prove this lemma 1. So proof of lemma 1. So we have to solve a Dolbeault problem. So first I'll set this Dolbeault problem up correctly, right? So the first thing you notice is that it's possible to extend f just by, right, so even before that, by applying a translations and a linear and also a linear transformation, we can assume that L is simply the hyperplane cut out by this equation Zn equals 0, right? So this can be done, again, just by translating and perhaps applying a linear transformation. Okay, so once you do this, there is a trivial extension of this small f to a small neighborhood of L simply by extending constantly in the Zn direction. But you can only do this for a small neighborhood. So there exists a U, open subset of X, such that U contains L intersect omega, such that the extension GZG, as I said, you just simply extend trivial in the Zn direction. This is how you define G, and such a G is going to be holomorphic on U, right? So read the picture. Maybe I can do a picture here. So this is omega. And then this is going to be L, and then such a U will be a small neighborhood here. So this could be your U, and then here you extend F to G, so G exists here in U in this way. So this is okay to do. Okay, good. So now what you do is you want the global extension, so you need to do a cutoff. So let's say delta, or maybe rho, be a smooth cutoff function on omega, such that rho is identically equal to 1 near, so in a neighborhood of L intersect omega. So now let, I suppose you can say capital G be equal to rho times small g, So now we get that this is obviously smooth on omega. It's not holomorphic, but at least when you restrict it to omega intersect L, we will get back small f. So now the last step is to fix this G to be holomorphic. So for this, so really correct this G to be holomorphic. For this, we solve the following Dolbeault problem. So bear with me. So now let psi be a smooth function in omega such that del bar of psi is equal to 1 over Zn times del bar rho times G. So this is a closed one form. You were initially slightly concerned that this 1 over Zn makes a pole, so smoothness is ruined, but 1 over Zn is obviously vanishing on the L, and rho is identically equal to 1 on L, so del bar of rho is going to vanish in a neighborhood of L. So this is actually smooth. So it's a smooth closed one form. So psi exists simply because of the fact we have this condition. Okay, so now set up capital F to be G minus Zn times psi. So in other words, rho times G minus Zn times psi. So since Zn vanishes on L, we get that F restricted to L intersect omega is indeed small f. And to verify holomorphicity, let's see, what's del bar of f? So del bar of f is going to be, so small g is holomorphic where defined. So it will, the first term will be del bar of rho times g. And also Zn is holomorphic where defined. So the second term will be Zn times del bar of psi. But del bar solves, so we have this del bar equation for psi. So if we move some terms left and right, we immediately see that this is identically equal to 0. So f is indeed holomorphic. So we are done. It's first lemma. Now, the second lemma I'll prove would be related to the first one. Perhaps not immediately this can be seen, but the proof is very closely related. So let's call this a lemma 2. So lemma 2 says in the same setup, now assume that actually all these cohomology groups of omega vanish. So for q in minus 1. So in that case, we actually get that the 0q cohomology groups of omega intersect L also vanish for all q in 1 n minus 2. Okay. This. Draw a nicer separator here. Okay. So let's try to prove this. So vanishing Dolbeault cohomology of omega, does that imply vanishing cohomology of omega intersect L? Oops. So let's pick a phi, which is a closed form. So smooth 0q form on omega intersect L. As I said, it's closed. Okay, so now I want to show that phi is exact. Now, before I do that, I will first extend phi to a capital phi on omega in such a way that the extension is also closed. So for this, we have to solve again the del bar problem. And the way we do this, we essentially use the exact setup from the previous lemma. So using setup of previous proof. So now let me maybe a chi as a 0 q minus 1 form, such that del bar of chi is equal to none other than 1 over Zn times del bar rho times capital phi, where capital phi is trivial extension of small phi to this neighborhood u in omega of L. So it's the same setup. We extend small phi to capital Phi trivially, then multiply with the rho, and again, divide with negative 1 over Zn. And then for the same reason, again, this will be a closed 0 q plus 1 form. So since we have vanishing cohomology here in omega, we can solve this del bar problem. Okay, so there exists this smooth chi. So now let me introduce the following form. So let alpha be the following global form. So let it be rho times phi plus Zn times chi. So this is a smooth 0q form in omega. Let's see what happens if I restrict it to L intersect omega. So this is identically equal to 1 on L intersect omega. So I would just get phi restricted to L intersect omega, capital Phi. Also, Zn is identically equal to 0 on L. So this is going to be just simply small phi, the form I started with. And let's see if I have closeness as I proposed. So this is going to be del bar rho times capital Phi, sorry, wedge capital Phi. When I hit the capital Phi with del bar, I just get 0 because the capital Phi is the trivial extension in the Zn direction of small phi. And similarly, in the second component, I get plus Zn times del bar of chi. So again, by the defining equation of chi, I get that this is identically equal to 0 on omega. So alpha is indeed a closed form here. So I can just simply use the fact now that all these Dolbeault cohomology groups are 0. So there exists a form beta 0q minus 1 in omega, such that del bar of beta is equal to alpha. But again, what was alpha? Alpha was okay. So instead, let's just restrict everything now to omega intersect L, and then what we will get is that del bar of beta restricted to L is equal to alpha restricted to L, but that is just simply phi by what I just noticed. So then we're done, right? So because we started out with a closed form phi, and we showed that actually such a phi is exact, right? So lemma 2 is also proved. So now let me prove the reverse direction of this characterization of domains of holomorphy using Dolbeault cohomology. All right, so let me call this a proposition. So I'm going to show that if these groups vanish for q in between 1 and n minus 1, then omega is a domain Okay, so let me give a quick proof. Okay, now with the aid of lemma 1 and lemma 2, we can give a neat argument here. And the argument is by induction on the dimension of n. So induction on a dimension. Right, so the case where the dimension is equal to 1. So in this case, our cohomology condition is completely vacuous, and that's okay because we know that in dimension 1, every domain is a domain of holomorphy. So this is the consequence of the Weierstrass theorem, among other things. Okay, so then the case n equals 1 is okay. So now let's assume that we know a proposition for dimension equals n minus 1. So assume that proposition holds for dimension is equal to n minus 1. And in addition, let's assume that omega is not a domain of holomorphy and derive a contradiction. Also assume omega is not domain of holomorphy. Okay, so this means by Cartan-Thallen, so I did a video on Cartan-Thallen. So by Cartan-Thallen, previous video, we get that omega is not holomorphically convex. So this means that there exists a compact set inside omega such that the analytic hull of K is not sitting compactly inside omega. So i.e., it touches the boundary of omega. So there exists a point Z on the boundary of omega that intersects the closure of the analytic hull. Okay. So now we use a hyperplane cut. So let L be a hyperplane in C to the n. Containing Z. There's an infinity of choices here. So by lemma 2, we get that H0Q of omega intersect L is always going to vanish for every choice of Q between 0 and n minus 2. So by induction step, this automatically implies that omega intersect L is a domain of holomorphy. So I will drive a contradiction with this using lemma 1. So let's pick an arbitrary holomorphic function in omega intersect L. So by lemma 1, there exists a capital F in holomorphic in omega extending small f. So f restricted to omega intersect L is equal to f. Okay, but by the proof of Cartan-Thallen, due to the fact that Z lies on the intersection of the boundary with the closure of the analytic hull, we know that capital F must extend holomorphically at the boundary point Z. So by the last step in the proof of Cartan-Thallen, you can go and review this step in my previous video. So by proof of Cartan-Thallen, we get that F extends, capital F extends at Z on the boundary of omega. But this means that the restriction of F to L, which is just small f, also extends at Z on the boundary of omega intersect L. But this is a contradiction, because this means that every holomorphic function on omega intersect L must extend at the boundary point Z. So we are done. Okay, so we proved one direction in this cohomological characterization of domains of holomorphy. Now, for the reverse direction, I'm just going to say in words here, it's much more difficult. And what one needs to do is first show that domains of holomorphy are examples of Stein manifolds, and moreover show, using difficult PDE techniques, Hermander techniques, that on domains of holomorphy, on Stein manifolds, every such cohomology group is going to vanish. So in many ways, Stein manifolds are the sort of the affine varieties of among the complex manifolds under some analogy. All right, thank you very much for your attention.